Hello and welcome to the webinar, The Future of the Smart Grid and Smart Home Energy Technologies, where we will be discussing lessons learned from a recently conducted smart home study. I am Kristen Larson, your host from the Center for Sustainable Energy, or CSE, and we have three great presenters today. John Clint, Director of Distributed Energy Resources from Alternative Energy Systems Consulting, or AESC, Stefan Barson, Senior Principal Energy Consultant from Itron, and James Tamarius, Senior Research Analyst from CSE. Each will be discussing their role in the study as well as noteworthy findings and lessons learned. The first presenter will be John Clint from AESC. He has been a practitioner in the energy and transportation fields. He researches, develops, and implements engineering and technological solutions to advance electrification and decarbonization strategies. He has evaluated many energy systems, including zero-emission vehicles, advanced energy storage systems, thermal and battery, intelligent loads, cogeneration, compressed air, and many others. The second presenter is Stefan Barson from Itron and has over 18 years of experience in mechanical and energy engineering, serving in design, analysis, and leadership roles. He has managed multiple grants under the California Solar Initiative Research, Design, and Development Program to integrate more solar to the grid and reduce the cost of solar energy. Prior to joining Itron, he led the development of cutting-edge solar and energy efficiency technologies at SunPower Corporation and Davis Energy Group. Last but not least is James Tamarius, who will present from CSE. James will be representing CSE and has worked as a research scientist at the intersection of climate and society for nearly 15 years. He has applied mathematical simulation and statistical techniques to energy, environmental, demographic, and health data, and he has published nearly 20 peer-reviewed scientific articles. At CSE, he has worked on projects in the area of distributed energy resources, EV infrastructure, EV rebate programs, and demand response. So now that everyone has a background of our presenters today, I will turn things over to John Clint.
Thank you, Kristen. In 2016, the California Energy Commission released a grant fund order intent on researching technologies that could help balance the grid usage by intelligently controlling behind the meter distributed energy resources. AESC and CSE responded and won the GFO, which officially titled the Advanced Intelligence to Enable an Integration of Residential Distributed Energy Resources. Once the project began recruitment, a customer-facing name was developed by the primary technologist Itron called the Smart Home Study, and that's what we'll refer to it from here on. Alternative Energy Systems Consulting is an energy engineering firm headquartered out of Carlsbad, California, near San Diego. We've been in business for 25 years. Our company is split into four main areas: engineering, such as audit work that we're doing for the County of LA, technologies such as grid intelligent projects that we're doing for PG&E, program implementation such as the facilitator for the State of California Energy Program, and software development such as Charge Ready portal for Southern California Edison. The Smart Home Study is multifold and layered. However, the main objective of the project is simply to develop a link between the smart home and smart grid using distributed intelligence to deliver user and grid level optimization of DERs and intelligent loads. The connected smart devices we have planned for the study included smart thermostats, solar photovoltaic, which were existing in the homes, electric vehicle charging, which we installed through the program, battery energy storage, which we installed through the program, heat pump water heaters, and pool pumps. We had to drop the heat pump water heaters and the pool pumps once we learned that in the San Diego area, which we were in, that most of the heaters were gas, and that most of the pool pumps that we ran into were actually controlled by VSD. The project scope is covered in four main areas. First, we wanted to conduct applied research of existing control technology, and in this case, it was Itron's IntelliSource system. For the project, we called it the Residential Distributed Energy Resource Management System, or RDERMS. The second area was to combine DER assets and loads under coordinated control. This included, once again, solar photovoltaic, battery energy storage, electric vehicle charging, and smart thermostats. Third, we wanted to create a real-world laboratory. To do this, we recruited 100 resident homes across SDG&E's territory to participate in the 12-month pilot study. The official study occurred between November 2018 and November 2019. As you can see on the right side here, we endeavored to include as many climate zones as we could within the utility service territory. Then last, we wanted to exercise both current and advanced tariff rate structures, specifically for the static tariff rates was the time of use. And then for the dynamic pricing tariff rates, we worked collaboratively with EPRI to integrate their signal. In order to achieve these lofty goals, AESC and CSC assembled a team of top experts. First off was the California Energy Commission. They provided the overall funding and oversight for the program. Next was Itron. They are the primary technologists. They developed the RDERMS technologies, recruited the participants, and installed the equipment. Next was Oxygen Initiative. They provided EV system integration and also performed and developed the clearinghouse to process pricing requests. Next is SDG&E, who graciously provided support and oversight and interaction with their customers as well. Then there's us, AESC. We are the project prime. We provided program administrative support, and we were also the overall solutions integrator. Next is Center for Sustainable Energy. They provided rate analysis and technology transfer support, amongst also providing general project direction and oversight. We worked collaboratively with the Electric Power Research Institute to integrate their dynamic price signal. And lastly, and probably most importantly, we recruited 100 customers who proved out to be early adopters and really make the program a success. The project plan was fairly simple. We wanted to demonstrate that a system could optimize load profiles for both the grid and for the customer. The project focused on the practical manifestations of the CEC grant front order goals, which was to flatten California's infamous duck curve. As you can see on the left side, the graph on the left side, this is a typical household. The red line demonstrates the combined usage of the household over a typical day, and the shape is roughly that of a profile of a duck. On the right is what we plan to achieve, and basically that was to flatten out that curve. We organized the project into phases to test the tariff impact. There are really two phases that we were able to test. First was the static tariff. These were the existing time of use rates that are available through SDG&E. They included the standard time of use rate and also solar and EV time of use rates. Next was the dynamic pricing signal from EPRI. Currently, this is a one-way transaction signal. Basically, it's a day-ahead hourly dynamic. The dynamic pricing signals are were also based on localized grid requirements with a factor that we developed or integrated into the process. The chart on the bottom shows the basic process flow. The very first thing we do is forecast the need in both loads and generation. Next, we establish targets optimized based on price and customer constraints and overall load requirements. And then lastly, we provide the control, including such things as charging and when to discharge and charge the battery and the scheduling of other controllable loads. Itron will go into the detail on the project results. However, a high-level summary is here. Number one, first, the concept works. We were able to intelligently control the homes. We were able to manage and shift load to optimize costs for the customer. We implemented smart EV charging to some extent. We did find some issues there that will need to be resolved in the future. We were successful in demonstrating tariff design could actually affect behavioral change, which was a major achievement. We did meet our recruitment goals. We were able to recruit 100 participants who made it through the entire pilot period that proved that there are early adopters out there. We showed that there was the ability to create successful device manufacturer partnerships, such as the relationship between Itron and Sonnen, the battery manufacturer. And then lastly, we were able to demonstrate that we could develop relationships to support strategic thinking and joint pursuit of goals. So the project identified for future consideration several things that need to be investigated. Number one was the communication protocols. These were huge barriers. Our ability to send signal to individual devices was problematic because of their native communication control structures. An interoperability standard could potentially help this, and this is something that needs to be looked at. The original design components need to integrate DER into their thinking so that they can actually have the physical and communication protocols set for an outside control. Storage monetization was another issue. When to effectively be able to use the battery was limited by tariff design, current tariff design. Sometimes we would like to operate the battery during when the sun was out during the solar period, and that was not possible with some of the current tariff structures. That needs to be looked into. We also found that different devices operate differently in regions with different customer constraints, and all of these have to be examined for the future. Scaling, there's a lot of customization that is going to be required before this project or this product is scalable. We found that at customer sites that many were not acceptable just based on their existing layout. So that needs to be overcome. And lastly, transactive energy complexities. For there ever to be true real-time pricing, it's going to require a massive amount of thought and planning. It's a very complex subject, and that two-way communications between individual homes or an aggregation of homes is going to require an understanding of the interactions and the complexities, and that's going to take some additional thought. Now, to look into the more details of this project, I'm going to turn things over to Stefan Barson from Itron.
Thank you, John. So I will be presenting some of Itron's role in this project as Chief Technologist. A little background about Itron: we're a multinational energy services company, very much focused on providing services to utilities through metering and forecasting. Some fun facts: 75% of the power and electricity in the United States touches Itron technology, and over 80% of electricity consumption in North America is forecasted by Itron software. We provide a number of services from measurement, and for this project, and you see in that red box, we provide sensors, meters, and controls. And those controls are using the IntelliSource platform that was developed for demand response and has now been augmented to provide a DERMS, or Distributed Energy Resource Management system. We manage and analyze data, and for this project, we utilize some of our forecasting expertise and also the analytics expertise that can be broken down into both distributed intelligence for some intelligence built into meters, and then also centralized control and analyzation. We also collect and connect different networks, and then deliver results to our customers. So within each of these 100 homes, we installed a number of pieces of technology. We started with sensing, and for this we used the existing Itron meters that were installed by SDG&E at each of these customer houses. At a number of these houses, we also installed a new meter to directly meter the solar photovoltaic or PV generation. We communicated with these meters using gateways. These gateways provided us near real-time access to both the net load and where available solar generation data. Each of these 100 homes had at least one, or in the cases where we had PV generation metered, 2 gateways, each gateway connected to one of those meters. And then we installed at almost all 100 homes a smart thermostat. This thermostat allowed us to directly control and monitor HVAC consumption and usage. This allowed us to basically pre-cool the homes and then set back the temperatures during peak hours. At 30 homes, we installed a level 2 EV charger. The primary usage for these chargers was to delay charging into lower cost time periods. And then finally, we installed 30 Sonnen batteries at a number of these homes. These batteries really allow us to easily move load from high cost periods over to low cost periods. So all of these pieces of equipment were tied together with our IntelliSource platform and gave us the ability to see energy usage within the home and then control, again, the cooling loads, EV charging loads, and then use the batteries to further control load at a number of homes. As John mentioned, this project had 2 different price shapes or signals that we investigated. The primary one that we looked at, that we actually asked all the participants to switch to, was a time of use rate, or TOU. This was what we called phase 1. And on this slide, you see that shown as the red line. And for the summer period, which within San Diego is from June through the end of October. That price shape has basically a peak period from 4 p.m. to 9 p.m. We also investigated a dynamic rate. This was generated by EPRI as part of a sister grant that John also had mentioned, and we called this phase 2. We did this for 2 two-week periods that we focused near the end of the summer period. And those 2-week periods were in early September and also mid-October. And you see how different the dynamic price is than that time of use static price is. In this slide, you see the difference in winter. So in early November, we had one last 2-week period and primarily controlled the batteries differently based on that green dynamic price shape that is, as you can see, very different than the static red time of use period. For most of these customers, when you have that little of price differential, which we saw in phase 1, it doesn't make economic sense to operate the battery. So now I'll move on to some of the challenges we saw during installation and operation and customer education. We encountered some challenges with installing some of these pieces of equipment. And primarily these were around both installing the battery and the EV charger. At the top right, you see a full customer utility panel that does not have space to add a new circuit. In addition to this, many customer panels are limited in the total current they can carry, and especially in older homes with only 100 amp or 125 amp service. In addition, we need physical space for the circuit. And then as you see, the Sonnen battery takes up a fair bit of space in the garage. Additionally, with the batteries, those batteries need to know what the customer load is so that they can accurately discharge, because currently the interconnection rules do not allow the battery to discharge to the grid. So the battery has to know how much energy the home is consuming so that it does not export energy to the electricity grid. In addition to these installation challenges, we had a number of operational challenges. Some of the operational challenges were with maintaining connectivity, to control and meter DERs. And then one of the other challenges we encountered is that San Diego is incredibly temperate. It's warm in the winter and relatively cool in the summer. So that really limits how much you can do with a thermostat to shift load. Additionally, current California rules for net energy metering, or NEM, provide for grandfathering. Within California, we are switching all customers to a time of use rate, but depending if you have a NEM agreement, so if you have solar on your house, depending on when you installed that, you can have from 5 to 20 years of grandfathering into that volumetric rate. Understandably, many of our participants were reticent to switch, so that required a fair bit of customer education, and we were able to get approximately half of the customers to switch. The other very big factor is that batteries on net will increase your energy consumption. So if a customer has minimal evening or peak load, there's minimal benefit from adding a battery to further reduce that load. What you see on this graph is a customer that does have substantial evening load, and then we were able to significantly reduce that load. And now I'll move into displaying some of the results that we have by what we call tier. So we broke our participants into 4 different tiers. The first tier are those that only received a thermostat and also a gateway and, as appropriate, a meter. Of these, we had approximately 50 customers. And for these customers, that's tier 1, the second set of bars, we did see some % reduction in peak energy use. Tier 2 were the customers that received both a thermostat and an electric vehicle charger. These did not see as much of a demand reduction as even the tier 1 customers. And as you'll see in later slides, we actually saw a significant increase in overall usage for these tier 2 customers. And the 4th set of bars is the tier 3 demand reductions during peak hours. These are the customers that received both a thermostat and a battery, and these are the customers that saw the biggest peak reductions because, as I mentioned earlier, batteries provide a great deal of flexibility of how you move your loads around. And then finally, in tier 4 are where we had approximately 10 participants. These are the customers that received the full suite. So they received gateways and meters, but also a thermostat, an electric vehicle charger, and a battery. And these saw slightly lower peak reductions than those that just received a battery. But again, in many cases, this is because those customers actually increased their energy consumption because they started charging their vehicles more at home and using electricity as a transportation fuel. And this slide shows the average load shapes for the baseline, which is shown in red, and then the study period, which is shown in yellow. So again, tier 1 customers are those that just received a thermostat, and you see very minimal load shapes. Tier 2 customers see some peak reduction during those hours. It doesn't show up great on this graph, but you also see an increase in energy consumption during off hours. And you see very similar results for the tier 3 and 4 customers, where the battery, be it the stationary battery or the vehicle battery, is being charged at midnight, and the peak load is being reduced primarily by the battery of basically discharging during that 4 to 9 p.m. window. As I mentioned, the overall energy use for many of these customers actually went up. For customers in tiers 2 and 4 that received a level 2 EV charger, we believe, again, this is because customers are charging more at their home and either not charging publicly or not using as much gas. And then for tier 3 and 4 customers that received a battery, that battery on net increases energy consumption. But it allows you to use your energy in more efficient or lower cost periods. In this slide, you see some of the cost impacts of what basically the operation of these devices had on customer costs. This is on the monthly average utility bill. And again, the baseline, which is the pre-study period, is shown in red. And then the study period is shown in yellow. And this is both the effect of switching rates, so switching from the rate the customers were on to a time of use rate, and then also the operation of the device. So on this chart is a scatter plot showing on the x-axis the baseline monthly utility cost that on average each of these customers was paying. And in some cases, these customers had a negative cost because they were generating more energy on average than they were consuming. And then on the y-axis, we have plotted what the monthly savings were if it's positive, or if it's negative, an additional cost, because those bar charts I showed earlier were averages, and you see a great sort of disparity or variation in how much customers could save by switching rates and also using the DER technology. This basically, the more customer consumed before the study, the more they could save during the study. And you can, but conversely, customers that had a negative bill before the study really, for the most part, did not save and actually had to increase their costs, because on a tiered rate, if you're a net exporter, you're more likely to save more or have more negative savings than if you were not. And so that's sort of the impact on the customer. What was the impact to the utility cost? So we also looked at what the impact on what the utility cost would be for, again, the baseline. In this case, it's shown in blue, and then during the study period shown in green. And the costs that we used for this were the CPUC, or California Public Utility Commission, marginal costs for San Diego that vary by hour and month and year. And what you'll see is that for thermostats, it was something of a wash. For customers that receive batteries, we see a significant reduction in cost, in the utility cost, that matches what we saw, and somewhat to the reductions in cost we saw to the customer. So customers that in tiers 3 and 4, the customer on average saved money, and the utility on average saved money serving those customers. So that's the proverbial win-win. Customers in tier 2 that only received a thermostat and an EV saw a little bit different result. And for these customers, you see that the utility actually ended up spending more money to service these customers. Now, part of that is because these customers increased their net consumption. Again, more charging at home and more use of electricity for driving their vehicle than using gas. The other aspect of this was due to the variation between the utility marginal price and the utility rate that the customer is seeing. The utility marginal cost, which is the line in yellow, has a much more pronounced peak in September. You see that that price has a much of a spike around hour 17, which would be 5 p.m. And that spike is much more pronounced than that basically utility rate. And that combined with the increase and net usage is what's driving those tier 2 customers to have on average a higher cost to the utility. Again, because they're using more energy and the relative mismatch between the utility price signal and the time of use rate. So based on our experience and the results from this project, we have a few key findings or results. And the first is that DER controls can change customer load shapes. Based on price signals, we can show that we can reduce peak demand and then shift load to lower price hours. Additionally, we have shown that by automating the control of DERs in response to time of use rates can benefit both customers and utilities. However, in some cases, due to a mismatch between the time of use rate and the utility cost, you can see opposite results where the customer could save money and the utility would actually have a higher cost. Additionally, connectivity and communications are very important to efforts like this. Use of the utility AMI network should aid with increasing reliable connectivity, and standards for communications and control should aid with scalability of being able to scale to new devices and reducing the need for customization for each individual device manufacturer. And these results are very dependent on rates. As mentioned, when your time of use rate and utility costs are not fully aligned, you can see benefits to one and costs to another. In addition, current NEM agreements that compensate customers at very near or at their retail rate don't provide an incentive to shift load away from, or increase load or shift export away from the middle of the day. So rates right now really help pushing down the head of the duct, but not so much the belly of the duct. And then finally, EV chargers and batteries will likely increase total energy consumption. However, smart management of those devices can reduce both customer and utility costs and conceivably aid with utility or renewable energy integration. And now I will hand things over to James from the Center for Sustainable Energy to talk about some of the tariff analysis and other analyses that CSE did.
All right, well, thank you, Stefan. So in this section of the webinar, we're going to discuss 3 analyses that we performed over the course of the project. And although these these analyses are related, they are distinct. And overall, these analyses had 2 broad goals. 1, to determine the value of residential DER management systems, or RDERMs, for both customers and the grid. And 2, evaluate the potential of novel price signals to encourage residential customers to shift demand to periods of high renewable generation. So in this first analysis, we will discuss the potential value of RDERMs. Specifically, we wanted to show the potential impact of optimizing the operational schedules of energy storage and EV chargers, 2 of the primary components of RDERMs, to reduce both customer bills and grid costs. To do this, we used annual electricity usage data from households enrolled in the study, as well as simulated EV charging and energy storage loads. For each household, we simulated energy load profiles for 81 scenarios consisting of combinations of various EV commute distances, home battery storage capacities, vehicle types, and SDG&E rate structures. The rate structures evaluated included the EVTOU2 and the EVTOU5. The primary difference between EVTOU2 and EVTOU5 is that EVTOU5 has very low super off-peak rates, about 9 cents per kilowatt hour, and a monthly service fee of $16. Several EV models were used in the analysis to examine the impacts of their different battery energy capacities and efficiencies. Finally, the scenarios also included 3 energy storage capacity possibilities: no storage, 4 kilowatt hour, and 8 kilowatt hour storage. To estimate the value of RDERMS, we needed to develop an appropriate load profile for comparisons. Accordingly, we generated unoptimized load profiles for this purpose, where an EV load during the on-peak period was superimposed onto the observed household loads to simulate after-work charging. The unoptimized model had no energy storage systems as well. So in the figure above, you see that the average daily load for a theoretical household represented by the gray dotted line and the unoptimized load represented by the black line, with the simulated EV load added in orange during the on-peak period. This would have a significant effect on costs, obviously, given the relatively large increase in load would occur during the on-peak period. So we compared these unoptimized load profiles to optimized load profiles generated by superimposing optimized EV and energy storage loads onto the same observed load data. The optimized loads were determined using linear optimization techniques aimed at minimizing customer and/or grid costs. This figure shows generally what we would expect the average optimized load profile for a household to look like, with the EV and energy storage loads shifted to the super off-peak period and the energy storage discharging during the on-peak period to lower the net load and costs. By comparing the costs associated with the unoptimized load profile, the figure on the left, to the optimized profile, the figure on the right, across all households and across all 81 scenarios, we could estimate the value of two of the primary components of the RDERMS system, EV chargers and energy storage, as well as the impact of rate structures, commute distances, energy storage capacity on this value to the customer and the grid. So the results can be broken up into three sections: the impacts of rate structures, EV charging, and energy storage on customer and grid costs. Specifically, our analysis shows that whether we were minimizing grid costs or customer costs, operational schedules of the energy storage and EV chargers were highly similar. This indicates that the design of the current TOU rate structures offered by SDG&E incentivize customer to shift loads in ways that are also beneficial to the grid. That said, there are slight differences that exist between the TOU price signals and grid costs, which suggests that the TOU structure assessed could be improved to better reflect these costs. For instance, our analysis showed that utility costs could be decreased by incentivizing load to shift to the daytime hours. Also, low grid costs in the early morning hours are more concentrated than the flat rate offered by the TOU rates during the super off-peak period. Thus, a more granular rate structure could increase alignment between customer and grid costs for this period in particular. The value of RDERMS to both customers and grid costs was highly sensitive to the rate structure applied. Specifically, the analysis showed that delaying EV charging from evening on-peak period to super off-peak periods is a simple way of reducing customer costs and reducing grid impacts. This is particularly true for customers that have long commute distance and are on a rate structure with low super off-peak rates, such as EV TOU5. Indeed, the analysis shows that shifting EV load for a customer with 30-mile round-trip commute can save a customer over $500 per year when they are enrolled in the EV TOU5 rate. The analysis also shows that energy storage can reduce customers and grid costs when they charge and discharge in accordance with the rate structures. On average, optimized 8 kilowatt-hour energy storage systems save customers approximately $450 per year on EV TOU5. The EV TOU5 rate structure also provided the greatest reduction in grid impacts when energy storage was dispatched. However, this may not be an adequate return on investment for many customers, given the cost of energy storage systems, installation, management services, and battery degradation. Overall, modeling results indicate that current TOU rate structures offered by SDG&E allow considerable benefits to customers and the grid with optimized EV charging and energy storage dispatch. The potential savings to customer from RDERMS is greatest for households with large energy storage devices and that have large EV charging requirements and also have large household baseline loads. Finally, having a low-cost super off-peak period is essential for customer savings and return on investment for the RDERMS. So in this next part of the study, we designed a new residential rate structure that incentivizes customers to shift loads to reduce both utility costs and GHG emissions. Our first goal was to assess how strongly marginal avoided costs and marginal emissions are associated across time. Ideally, these costs would be perfectly associated and a rate structure could be designed that minimized both simultaneously. To accomplish this and the other tasks in the analysis, we used hourly marginal avoided costs for 2018 from the CPUC avoided cost calculator to estimate the costs associated with increases and decreases in load on the grid for any given hour. A time series of the marginal avoided costs are shown in the plot on the right in blue. We also use marginal emissions data for 2018. The marginal emissions data were generated and provided by WattTime and indicate the change in GHG emissions for a given load increase or decrease for 2018. These data are hourly and provided in metric tons of CO2 per megawatt hour. The time series of marginal emissions are shown in the plot on the bottom right in orange. And overall, these data show that marginal avoided costs and marginal emissions are positively associated. In other words, marginal avoided costs tend to be high when marginal emissions are high, and marginal avoided costs tend to be low when marginal emissions are low. However, there are periods where this association is not as strong. The plots on the right show the mean percentile rank of hourly marginal avoided costs in blue and marginal emissions in orange for 2018. Overall, the figure shows that in the spring, the scaled marginal emission values tend to be larger than the scaled marginal avoided costs during the overnight period, particularly between 9 p.m. and 3 a.m. In other words, increasing loads during this period will have a relatively small impact on utility costs, but would cause a more significant increase on GHG emissions. Thus, you could imagine a utility designing a rate structure that incentivizes customers to shift load to this period to reduce costs, but this could increase GHG emissions depending upon the period the load was shifted from, given the relatively high marginal emission rates. To design a rate structure that takes both marginal emissions and marginal avoided costs into account, the next step was to build a signal that combined both the marginal avoided costs and marginal emissions into a single signal. To combine these signals, we took the average of the scaled marginal emissions and marginal avoided costs to generate an index. The yellow line in this figure on the right shows this combined index by hour for each season in yellow. So basically, when the signal is high, it means that both marginal avoided costs and emissions are high during this time. And when the signal is low, it likely means that both marginal costs and emissions are low. When the values are moderate, it either means both marginal avoided costs and emissions are moderate, or one of them is high and the other is low. For reference, the green line indicates the prices corresponding to the EVTOU5 rate structure, which we saw in the last analysis. You can see that there are significant differences between the EVTOU5 rate structure and the combined index, suggesting that EVTOU5 may not balance the dual objectives of lowering emissions and utility costs as well as it could. So our next step was to examine how we could modify the EVTOU5 to follow the combined index more closely. So we created a modified rate structure that balances the marginal avoided costs and emissions while retaining the level of complexity and rate levels of EVTOU5. The level of complexity of the existing rate structure was retained to highlight how simple changes could better align the structure with the marginal avoided costs and emissions. To do this, the seasonal combined index values were mapped to the nearest percentile rank of the 6 unique time-dependent pricing levels assessed under the EVTOU5 tariff. So the figure on the right shows how the combined index values were mapped to these different pricing levels. And for simplicity, the schematic only shows 4 of the 6 pricing levels. This was performed for each season and for weekends and weekdays to mirror SDG&E rate structures. So the figure on the right shows the new rate structure in yellow produced by mapping the combined index to the EVTOU5 rate levels. The green line is the EVTOU5 rate structure for reference. Overall, the modified rate structure and EVTOU5 are highly similar. You can see in both rate structures, the highest rates are in the afternoon, evening of the summer, and the lowest rates occur in the overnight hours across each season. So this means that in general, the EVTOU5 promotes electricity usage patterns that will reduce both utility costs and GHG emissions. However, there is a notable difference as well between the rate structures. This difference is that the new or modified rate structure is characterized by super off-peak rates during the daytime in winter and summer, as well as a significant increase in these hours, again relative to EVTOU5, during the spring. These daytime periods coincide with high levels of solar generation and relatively low levels of demand, which decrease both utility costs and GHG emissions. There are a few other minor differences, such as reduced on-peak period in the summer, but the lower daytime rates across all seasons is the most significant. To understand the potential impacts of this new rate structure on costs and emissions, we used observed customer net usage profiles and simulated energy storage dispatch aimed at minimizing customer bills, and applied these both to EVTOU5 and the new modified rate structure. And what we found is that storage systems shifted energy and resulted in reduced emissions and utility costs relative to scenarios with no battery storage. In other words, both rate structures promoted energy usage that reduced GHG emissions. However, emissions reductions were 0.02 metric tons per year and 0.03 metric tons per year less on average per household for 4 and 8 kilowatt-hour systems, respectively, for the new modified rate structure. The reductions in emissions corresponding to the modified rate structure were due to an increase in daytime charging and a commensurate drop in early morning charging. The impact on utility costs was nearly equal across the rate structure. The analysis shows that the EVTOU5 rate structure corresponds in general with seasonal and daily variations in utility costs and emissions, thereby incentivizing customers to consume low cost and low GHG emissions energy from the grid. But there is opportunity to make slight modifications to the rate structure that can potentially reduce emissions further without significantly affecting utility costs. Okay, so now we move on to the last analysis we performed for this study. So one of the emerging issues for renewable integration is curtailment. Curtailment is a growing problem as more renewable capacity is added to the state's grid, with more curtailment in the first 5 months of 2019 than in all of 2015. So the objective of the second analysis was to assess trends in negative pricing events, and negative pricing events are an indicator of renewable electricity curtailment, and evaluate the potential economic benefits of customer participation in the CAISO LSR product to build load during these negative pricing events. Basically, the LSR product will compensate customers who employ behind-the-meter resources to bid load increases into the wholesale market during times of negative marginal pricing. We assume that customers are compensated with a negative wholesale market price for shifting flexible DER load, such as energy storage. For this analysis, we used 2018 CAISO real-time market prices for the local SDG&E sublab. Monthly and hourly trends of negative prices in the CAISO 5-minute real-time market were evaluated by summing the total duration of 5-minute intervals with negative prices. Accordingly, the negative prices for each 5-minute interval were converted to dollars per kilowatt and summed across the year to derive the maximum potential annual compensation per kilowatt. Since the available flexible capacity in a household would affect potential compensation, we evaluated it across a range of capacities. The figure on the top right shows the duration of negative pricing events by month in 2018. It can be seen that low demand and high solar generation results in negative pricing events over 5% of the time for some spring months, with limited negative pricing events in the summer. During the seasons with relatively high solar generation and low demand, negative pricing is most likely to occur in the daytime hours, as can be seen in the figure on the bottom right. However, although there was over 250 hours of negative pricing in the real-time market in 2018, over 50% of negative wholesale market prices were between -5 and $0 per megawatt hour. As such, the potential compensation to a residential customer was extremely low. For example, 10 kilowatts of flexible capacity, such as energy storage, that discharged at maximum capacity for all negative prices events totaled less than $20. Additionally, behind-the-meter resources would be required for customers to participate in the wholesale market. The added cost of such resources resulting from contracting scheduling coordinators and demand response providers would likely surpass the compensation of participating in the market, let alone the cost of acquiring a battery or other resources with load shifting capacity. As such, at this point, the LSR product is unlikely to encourage customers to invest in DER and shift loads during times of negative pricing. So overall, we performed 3 distinct but related analyses that examined the potential of DER management systems to reduce customer costs, utility costs, and GHG emissions. The main takeaways from our study are that DER management systems provide strong value to the customer and the grid on existing SDG&E TOU rates. For instance, customers with EVs that also have long commutes and have large storage batteries can save up to $1,000 annually while reducing utility costs and GHG emissions. We also found that existing TOU rate structures do not sufficiently promote energy usage during some of the daytime hours, especially in spring and winter, which typically corresponds to the cleanest energy. Lowering prices could incentivize load to be shifted to these hours and result in decreased GHG emissions with minimal impact on utility costs. Finally, we assess the potential compensation for residential customers participating in CAISO's upcoming LSR product that could compensate residential customers the negative wholesale market price for increasing loads during negative pricing events. We found that although negative pricing events are frequent, they provide little incentive for residential participation in the program. All right, and with that, I will hand it back to Kristen.
Great, thanks, James. And another big thank you to all of our presenters for sharing their experiences. Also, thank you to our viewers. And if you're interested in more information about the Smart Home Study, please check out the additional resources on CSE's website.